Okay, so when we started the chapter, which is mostly about limits, right? And we said there's two reasons we take limits. One is to solve what's called the tangent line problem. For that, we needed limits as x approaches some fixed number. And the last section was the tangent line problem. We solved that problem, right? Now we can find the slope of a graph at any point, right? We don't have the issue anymore. We need 2 points to calculate the slope. Okay, the other one was called the area problem. And for that, we're going to need limits as x, or in the case of a sequence, as n approaches infinity. And if you remember, what we said is if you got an irregularly shaped graph, this was the same picture we used for that, and you want to find the area underneath it, you don't have a formula for it. So usually what we'll do is start with some rectangles and find the area of these individual rectangles and then add them up. That'd be an approximation. Now, would it be accurate? Would it be telling exactly the area under the curve? No, but it would be a start. How could we make it more accurate? Increase the number of rectangles, right? As we increase the number of rectangles, each rectangle gets thinner, right? And as we keep going to more rectangles with less width and more rectangles with less width, eventually the width of the rectangles is approaching 0. The number of the rectangles is approaching infinity. Can we ever let the width of the rectangle go to 0? No, because then none of the rectangles would have any area, right? And you couldn't add them up at all. So we have to come up with a limiting process for when we do that. Now this is taking a curve. This is actually just a sine curve. And I'm going to approximate the area under the curve. And in between A and B, there's always like a left-hand limit or bound and a right-hand, or the interval. The interval is A to B. And we're going to add up the two rectangles, right? Each one will have a length and a width, or a width and a height, and we'll add them up. And as we do that, this here is the width of the rectangle, right? This is the width. I mean, it's the B minus A. It's this whole distance divided by 2, right? That's the width. And it'll be the same for both rectangles. Now, in order to find the height of the rectangle, actually you got a little bit of a decision to make, because it depends whether you're going to use your rectangles. I've set it so that the height of the rectangle is the value of the function on the right side of that interval, right? So here and here. But that's not always the way you do it. You could take the rectangle, like, and say, let's make it on the left side, the value of the function on the left side. Sometimes you do that. Then I'd be doing that. I wouldn't get the same area if I did it that way. Sometimes you use midpoint. So you could take it and go like halfway in between these two would be about right there. And I could take this one and go right there. Which one ends up being more accurate kind of depends on the shape of the graph that's underneath it. But for the purposes of this, we're using the right side of the interval. Right there and right there. So again, we're using the height of this rectangle, which might otherwise known as the length here, is the value of the function on the right side of the rectangle. So this is f of, right, and a plus, so you're starting here, and you're adding these widths, b minus a over 2. When the I equals 1, you're adding one width to the right of a. So that means go one width to the right, and that's the height of the rectangle. When I equals 2, you'll go 2 widths. Go once, twice, and that'll be the height of the rectangle. So this is the length or the height, whichever one you want. Let me